Hello students, today we are going to study a very interesting topic in electrostatic, and that topic is potential or potential energy. So first we will study about potential energy and then we will move to potential, which we call as electrostatic potential. So let us start. Here we have taken a charge capital Q, and this charge capital Q we call as source charge. So this capital Q is the symbol for the source charge we have taken, and this charge, which we are calling as a source charge, this is capped at origin. This is capped at the point naught or 0, 0, 0. That is what we call an origin in the coordinate system. So this we have capped at the origin, and say this origin we are taking at point P. So at point P we are considering a source charge capital Q. And if there is a source charge capital Q is capped at point P, then it will create an electric field. If you want to know about how the electric field is created, what is the effect of electric field, and how plus Q or minus Q differentiates in creating the electric field, then I have given the link of the lecture below, so you can go to the link and you can study easily about what is electric field. So for now, this charge is creating an electric field, and into the electric field of this source charge capital Q, we are bringing another charge which is positive, which we have denoted as plus Q. So this small q is a point charge, which we also call as a test charge. So this is the point charge, which is also a test charge. And if you want to go to the details of point charge or test charge, then you can again refer to the same lecture I have given below the link. But for now, the charge which is creating the field is taken as capital Q. And if small q is bring into the electric field of the source charge, then we call this small q as a test charge. So we are bringing this charge positive small q from any point R, right? So if we want to bring this here, then we have to do some work against the repulsive force, because there is repulsive force which is acting between this charge capital Q and small q. So these are repulsing each other. So if we want to bring this charge small q close to capital Q, then we have to do some work. And the work we are doing, so what is the work we are doing? The work actually we are doing is against the electric field, because we are bringing these two charge close together. This q is kept fixed as the origin, and small q we want to bring close to this. So we have to work against the electric field of charge capital Q. And this work or this force we have to do externally, the force we have to apply is in the opposite direction of the force due to the electric field. So what we conclude from this relation, that F external is equal to minus of Fe, we conclude that the force which is external force which is doing the work, and it is equal to the negative of the work done by the electric force. What we conclude, that the work done by this external force will be equal to the negative of the work done by the electric force. And this work done, which is an external work done, it is stored in the form of potential energy. I am repeating, the work done externally is stored in the form of potential energy. And where does this potential energy goes? Where it is stored? Let's know. This potential energy is stored, or this form of potential energy is stored for the charge plus Q, which was our test charge. Because we are doing the work on the test charge, so the work done externally is stored in the form of potential energy of charge plus Q. Hope it is clear till now. So next, what happens? When we remove this external force, why we are applying this external force? Yes, you are right. We are applying this external force because we are trying to bring charge plus Q close to the source charge, capital Q. So we have to work against the electric field of Q. Now what do you want to do? We want to remove this external force. So at point P, if we remove the external force, the electric force will take the charge away from minus Q. Our external force is removed. So now the only force that is working is the electric force. And what is the direction of this electric force? It is opposite to the work we have done. So what it will do? The electric force will take the charge away from capital Q. Now it will move like this. When the external force is removed, then this charge plus Q, the force, electric force, will act in the opposite direction because there is a minus sign. So this force will take the charge plus Q away from this source charge. And what happens to the energy stored in this charge plus Q? And the energy stored, which is we call as a potential energy, it is used to provide kinetic energy to charge Q in such a way that the total energy is conserved. So when we remove this external force, the only force which is working is the electric force, which is in the negative direction. So it will take the charge plus Q away from the charge capital Q, and the potential energy which was stored in charge plus Q is now converted into the kinetic energy of charge plus Q, and hence the charge plus Q moves away from the source charge capital Q. And this follows the law of conservation of energy for the charge small q, because the total energy, that is the sum of potential energy and kinetic energy, it remains conserved. So the energy conservation law is followed here. If we want to write down in terms of work, then the work done in taking the charge from point R to point P, it is always equal to the work done, and work done is equal to force multiplied with displacement. So the force which is working is the external force, and say dr is the displacement, and we have to integrate. Integrate means we are taking all those small sums for this distance, because F external is the external force we are using, and dr represents the distance we have traveled. So how much the distance we have traveled? We have traveled the distance from R to P. So the work done in bringing the charge from the point R to point P is WRP, and this is equal to force into displacement. Force is external force, and the distance is integrated from R to P. We have integrated the total distance from point R to point P. And this may also be written as our integration remains the same, R to P, and dr also remains the same, but this external force is equal to the negative of electric force. So here we can write down F external is equal to minus of electric force. So the work done is minus of integration r to p fe dot dr. So this is how we can calculate the work done in bringing a charge from any point capital R to the point P, and this work done is stored in the form of potential energy. So if we know the electric force, then we can calculate the potential energy. So what we conclude from this, that the work done in bringing the charge plus Q from point R to point P is the external force multiplied with the distance R to P, and this is equal to the negative of electric force, which is working due to the charge, plus Q, which is at origin, and it is multiplied with the distance. So here we can calculate the work done, which is equal to total potential energy, and if we know the electric field which is created due to charge plus Q, then we can also calculate it, that if we bring any charge close to it, then how much is the work done, what is the force acting. So from the force acting, we can calculate the work done, and in result the work done will give us the potential energy. So now we know that why there is a potential energy in the test charge Q, and this test charge Q we take always is smaller than our source charge capital Q. So both are of similar charges, so there's a force of repulsion. We have to apply some external force to move them together, and if we're applying some force, then there is work done in bringing these charges together, and the work done is stored in the form of potential energy of small q that we have done. So that we call as potential energy. So potential energy, how come this potential energy gives us the potential energy difference? Let's see. At every point in electric field, charge Q has some electrostatic potential, because this discharge Q is always in the electric field which is created by the charge capital Q, which is the source charge. So at any point in the electric field, charge Q has some electrostatic potential. It is always there present for the charge small q. And when the work is done in bringing these charges, when we do some work, that is the external work done, then this external work done, the potential energy increased by an equal amount. Whenever some external work is done on this charge small q, then the potential energy of small q is increased by an equal amount. And this amount which is added, it is equal to the potential energy difference between two given points. Say we have just done with points R and P. So if we calculate the potential energy of charge Q at this point and the potential energy of charge Q at this point, then the difference of electrostatic potential energy between these 2 points give us the potential energy difference. This is in short, I have written potential energy difference. So this is the potential energy difference between any 2 points. So let us say that we will consider the same case as we have done just now, that initially our point Q, let us redraw what we have done. We are having a source charge, and the source charge we are taking it positive, and this is at any point P, and this was our point R, and we are taking this plus Q from point R to point P. Fine. So we calculate the potential energy of Q at point R, and then we calculate the potential energy of Q at point P, and then we find the difference. So the symbol we use for potential energy is always capital U. So U defines the potential energy, and here the electrostatic potential energy. So the difference in potential energy is denoted with delta U. Delta shows the difference and capital U shows the potential energy. So the difference in potential energy is equal to the potential energy, which is electrostatic potential energy at point P, minus electrostatic potential energy at point R. So if we take the difference of potential energy at the final point and initial point, then we get the potential energy difference. And what will be the difference equal to? As I told you that this difference will be equal to the work done in bringing the charge from point R to point P, because that is the work done which is added in the form of potential energy to this charge small q. So what we conclude? That the potential energy difference is equal to the work done by an external force in moving that charge from point R to point P. Right? Should I repeat it once again? Okay, then the work done by an external force on moving the charge from one point to another in an electric field. That is the definition of potential energy difference. Now, whenever we are calculating this potential energy difference, we have to consider certain points. What are these points? So, let us move to points we should always remember whenever we are calculating the potential energy difference. The first and the very important point is the external force which is acting is a conservative force. The force which is our external force, this F external we are applying. Which type of force is this? This is always a conservative force. Conservative force means the work done by the force does not depend on the path chosen. That means it depends only on the initial and final position. The external force is a conservative force. That means it will depend only on the initial and final position, and it is independent of the path taken. So if we want to represent this as a conservative force, then we take the points. So if this is our point R and this is our point P, and we are bringing this charge by doing some work from point R to point P. So this is the path 1 we have chosen, or maybe we can take this path, we can call as this as path 2, or we can take this path, this may be called as path 3, or this may be through this path, maybe path 4 or path 5. So we have to only calculate the difference in potential energy between this and this, that is UP minus UR, and it does not depend on the path we have chosen. Now let us move on to our second point, that is the work done is equal to the difference in potential energy, that is the potential energy at point P minus potential energy at point R, and that is equal to our work done. So what does it mean? That the potential energy of charge Q at point, this may be any point, so at a point in the presence of electric field is the work done by the external force in bringing the charge from any initial point to the final point. That is our initial point and this was our final point. So these are the 2 points we have taken, and if we take the initial point at infinity, what happens? We take the initial point from where we are bringing the charge small q. We take this initial point at the position of infinity. Then what happens? If this is at infinity, then we define that the work done by the external force in bringing the charge from infinity to any point is equal to the work done. So keeping in mind these 2 points, we can define the electrostatic potential. The symbol for electrostatic potential is capital V. So we got the definition of electrostatic potential as work done by an external force in bringing a unit positive charge from infinity to a point is called the electrostatic potential. Initially we have taken 2 points, P was the initial point we have taken, and R was our final point. This was our point P, and R was our final point. Here we are having a source charge capital Q, and the distance here we are bringing the test charge plus Q. And from point P to R we are bringing our charge plus Q. So this initial point P, we have taken this point to infinity. That means now we are bringing our test charge from infinity to any point R. So the work done is equal to the electrostatic potential at point P minus electrostatic potential at point R, and this is given as the test charge multiplied with So now we can say that the total work done is equal to electrostatic potential energy at point P minus electrostatic potential energy at point R. Here U denotes the potential energy. So the work done is equal to the difference in potential energy, and this will be written as our test charge Q multiplied with electrostatic potential at point P minus electrostatic potential at point R, or this will be written as Q, and this difference in electrostatic potential is written as delta V. Delta V shows the difference in potential. So if we want to calculate the difference in potential, Vp minus Vr, electrostatic potential at point P and electrostatic potential at point R, this is equal to Up from this equation. Up minus Ur upon Q. What does it mean? That if you want to calculate the difference in electrostatic potential, then you may simply write the difference in electrostatic potential energy divided with the charge, test charge, small q. And to define this, to have a definition of electrostatic potential, we have taken this test charge as a unit charge, means it is having a value of unity. So if we take this test charge as a unit charge, then the difference in potential energy, which is the electrostatic potential energy, is equal to the difference in electrostatic potential. So now we can see this definition once again, that the work done by an external force in bringing a unit positive charge from infinity to a point is the electrostatic potential. That means if our charge is unity, then the electrostatic potential energy becomes equal to the electrostatic potential. Now if we know the electrostatic potential energy, we can define the potential, and if we know the potential, then obviously we can define the electrostatic potential energy. So now we are much familiar with what is electrostatic potential, what is electrostatic potential energy, and what is the relation between potential energy and potential. Potential due to a point charge. You will take a point charge, small q, and we want to calculate the electrostatic potential. And electrostatic potential is denoted with the symbol capital V. So we want to calculate this electrostatic potential for our test charge small q. So as we know that if we know the electrostatic potential energy, then we can calculate this electrostatic potential, and the electrostatic potential energy is equal to the work done, which is the external work done. So we will simply calculate the external work done, and that will give us the electrostatic potential. So for this, go to the diagram. Here we have taken a charge, test charge small q, and this test charge small q is initially we have taken a point as an infinity. So from infinity it comes down to the point P dash, and from P dash it comes to the point P. So these are the 3 points we are considering for the test charge. And to create the electric field, we have taken a source charge, which is a positive capital Q, and the point P is at a distance of small r. The distance between Q and P is small r, and the next point is P dash. So the distance between Q and P dash is r dash, And if we take the distance between P and P dash, it is R dash minus R. So delta R dash we have taken as delta R dash is the difference of distance between Q to P dash minus Q to P. So this gives us the distance between 2 points P and P dash. So these are the two distances we have taken. Q to P is R and Q to P dash is R dash. And we have taken the third point at infinity. So what happens then? Let us see. So if we want to bring this discharge from point infinity to the point P, and the point P dash is intermediate between infinity and P. So if we want to determine the potential at any point P, which is at a distance of small r from Q, then this is equal to the work done in bringing a unit positive charge from infinity to point P. Fine. We have taken this charge as a unit charge. So our electrostatic potential energy will be equal to the electrostatic potential energy. Our electrostatic potential will be equal to the electrostatic potential energy, and this will be equal to the work done because Q is 1. So V is equal to U and U is in turn equal to the work done. So let us calculate the work done, and for work done we have to know two things. First is the force and second is the displacement. So let us calculate the force and let us calculate the displacement. So to calculate the displacement we have taken any point P dash, which is intermediate between the initial point at infinity and the final point at point P. So P dash is the middle point or P dash is the intermediate point. So at the intermediate point on the path, we want to calculate the electrostatic force. This is the electrostatic force which is working due to the presence of this capital Q. So if we calculate the electrostatic force, this is equal to F is equal to K, Q1, Q2 over R square. So put the value of Q, one is capital Q and this small q is having a value of 1. So this is Q1 into Q2 and this is our constant 4 pi epsilon naught, and the distance is R dash because the distance between this source charge Q and point P dash is R dash. So this will become R dash square and the direction is R dash cap. If you want to know how we calculate this formula for electric force, then you can go to the lecture, my previous lecture on electric force and electric field. So the link I have given below, but for right now you can say that the force is equal to K Q1 Q2 over R square. K is having the value of 4 pi epsilon naught. One charge is capital Q, another charge is having a value of unity, so small q is having a value of 1, and the distance between Q and P dash is R dash, so R dash square, and the distance is R dash cap. So this is the force. Now next we want to calculate the work done against this force, because this is the electric force, so the work will be done against the electric force. So the work done against this force, so this is the force. So now we want to calculate the work done. So the work done is equal to, say, the work done, which is a part of the work done, because we are bringing this discharge from P dash to P. So the work done is equal to force into displacement. Force we know, and this work done is against the force. So this is with the symbol minus Q. 4 pi epsilon naught R dash square R dash cap, and the displacement between these 2 points is delta R dash. So this is force multiplied displacement, so this will give us the work, and this work done is in the opposite direction of the electric force. Right? And if we take this distance delta R dash, it is very less than 0, then our work done will obviously be positive. So we'll have a positive work done if delta R dash is having some negative value. So we have just calculated the amount of a part of the work done, and from this we can easily calculate the total work done. Because if we know a part of work done, then we can integrate this and we can have the total work done W. So the total work done W is equal to integration over the whole part. We are bringing the test charge from where to where? Yes, from infinity to point P. So this is infinity and point P is having a distance of small r. And put the value of force minus Q upon 4 pi epsilon naught R dash squared, and this we can write on because we are integrating, so we can write on this delta R dash as dr dash. So if we integrate this with respect to R dash, then we will have a minus sign. So this minus cancels out with this becomes plus. So this is equal to Q upon 4 pi epsilon naught R dash. Because if you integrate this, you will have minus 1 upon R dash. So minus minus makes a plus, and this reduces to Q upon 4 pi epsilon naught R dash. This is the total work done. And if you want to put the limits, so the limits will be from infinity to R. So just put the limits on this R dash. If it is infinity, then that becomes 0. And if it is R, then this R dash becomes R. So this is equal to put the limits, this is Q upon 4 pi epsilon naught R. This is the total work done in bringing the charge from infinity to any point P. So we can say that the potential at point P due to charge capital Q is the electrostatic potential V is equal to Q upon 4 pi epsilon naught R. So at any point P, we have taken the electrostatic potential capital V is equal to Q upon 4 pi epsilon naught R. That means our electrostatic potential depends on the distance R. So we can say that this electrostatic potential is a function of the distance. This is how we write on a function. This is electrostatic potential V. So this V depends on R. So V may be written as a function of R. So finally we can write down the electrostatic potential has the value of Q upon 4 pi epsilon naught R. If we have any source charge capital Q which is creating an electric field, then at a distance of small r, it will have the electrostatic potential of Q upon 4 pi epsilon naught R. So you should be happy now because you know what is electrostatic potential energy, what is electrostatic potential, what is the formula for electrostatic potential, how the electrostatic potential energy is related to the work done, how it is related to the external electric field, how it is related to the electric field, how it is related to the external force that is applied, and how the potential energy and electrostatic potential are related to each other, and how we can calculate the expression for electrostatic potential simply by calculating the work done and keeping the point charge as unity. And now we can start with potential due to electric dipole. We have just calculated the potential due to a test charge. Now we will have a dipole and we will calculate that what is the potential which is created due to this electric dipole. That means instead of a single charge, we are taking it as a source charge. Now we will have two charges which are equal and opposite. That is a dipole. And if you want to know more about dipole, I have given a link of the lecture about the dipole and dipole moment, so you can go through this. But for now, dipole is simply a pair of charges which is equal in magnitude and opposite in charge. So let us know that what is the potential. So let us first draw a dipole and then calculate the potential at any point P. We take a dipole. This figure shows a dipole where we have the charge plus Q and second charge minus Q, and these two charge are at a total distance of 2a. So here we have taken the midpoint of these two. So the distance from this midpoint to this plus Q is a, and from minus Q is again a. And here we have taken any point P which is at a distance of small r from the center of the dipole. So the distance between the center and the point P is small r. The distance between the positive charge and point P is r1, and the distance from minus Q and point P is r2. So this is how a dipole we have taken, and from this dipole we want to calculate the electric field at any point P. And we have taken this distance 2a as a small distance, that is the distance between the two charges of the dipole. So we have taken this 2a as a small distance between these two, and the total charge due to this dipole, if we take total charge, because in dipole we have plus Q and minus Q, so the total charge is 0. Why is it 0? Because dipole has plus Q and minus Q. So that makes a total of 0. So that is why we have taken total charge as 0. Now electric field of this dipole. If you want to know the derivation of electric field of a dipole, I have given the link below for a lecture on electric field of a dipole, which has all the derivation and the explanation, so you can quickly go through it. And for now we can say that the electric field of a dipole at any point is proportional to the inverse of cube of the distance. So the electric field is inversely proportional to 1 upon r cube. R is the distance. So we have taken the center of the dipole at the point, and we can take this point as the origin. So the center of the dipole may be considered to be situated at the origin. So the electric field obeys the superposition principle. So the potential due to dipole is the sum of potential due to charge plus Q and charge minus Q. What does it mean? Because we are having two charges, plus Q here and minus Q here, and at point P we want to calculate the electrostatic potential V. So this total electrostatic potential will be the sum of electrostatic potential due to plus Q and electrostatic potential due to minus Q. So we can write down both the potential and we can simply add them up. So electrostatic potential due to charge plus Q will be K Q upon R. Put the value. K is 1 upon 4 pi epsilon naught. Epsilon naught is the permittivity of free space, and Q is Q, and this becomes the distance from plus Q charges R1. Similarly, we can write down the electrostatic potential due to charge minus Q. It is again the formula KQ upon R, because the same quantity we are calculating, so formula is same. So here the charge is minus Q and K is 4 pi epsilon naught, and R is the distance from minus Q to P, so this is R2. Now we want to calculate the total electrostatic potential. We use the vector sum of plus Q and minus Q, so we use the principle of superposition, and we get this as, this is taken as a common 1 upon 4 pi epsilon naught. Then we have Q upon R1 minus Q upon R2. So this expression we get. So here R1 and R2 are the distances of point from P to plus Q and P to minus Q. Now we want to calculate the value of this R1 and R2. So to calculate, we go to the diagram. Here you can see R1 and here you can see R2. So if you want to calculate the distance R1, then we can take this triangle. For considering a triangle, because this is the origin, we can simply write this point as O. So you have a triangle QOP or POQ. So from this triangle, since this is perpendicular and this angle we can take as theta, so we can simply use the equation to calculate the distance r1. So from here we can write down, taking this angle is theta, and the distance between O and P is r, small r. So we can write down r1 square is equal to r square plus this distance between O and Q is A. So the square of this distance minus 2ar cos theta. That is very easy for all of you to write it down. If you take this triangle, similarly we can take the triangle O minus QP, and we can write down r2 square is equal to r square plus a square plus 2ar cos theta, right? And these are the two equations we have written for the distance r1, and from here we can write down r1 square is equal to r square, we can take as common, and we are left with 1 minus 2a cos theta upon r, because r square is common, and the last term will be plus a square upon r square. Similarly, we can write down r2 square, this is equal to r square 1 plus 2a cos theta upon r plus a square upon r square. Now, since the condition is that a is very smaller in comparison to small r, so we can neglect this last term in both the equations. So we can write down r1 square simply as r square 1 minus 2a cos theta upon r. So this is the approximation we can take. If this is approximately equal to this approximation we can take if we are taking a is very small than r. Similarly, r2 square is approximately equal to r square 1 plus 2a cos theta upon r. So now we have the value of r1 and r2, and we can put it into these equations, right? So let us solve them. What we can do, we can write this equation as we want the value of r1 here and we want the value of r2 here, but here we are having the square and we need the value of 1 upon r1 and 1 upon r2, so we make it 1 upon r1. From this equation 1 upon r1, that means we have to simply reverse the equation, inverse the equation, and we have to take a square root. So this is approximately equal to 1 upon r and 1 minus 2a cos theta upon r to the power minus half. We have taken under root and we have just used the equation. Now we can simply use the Binomial Theorem. 1 plus x to the power n is equal to 1 plus nx. So this may again be written as 1 upon r, then 1 minus, then the power comes here, minus half, and 2a cos theta upon r. So this is the equation. Now see in this equation what cancels out, minus minus becomes plus and 2 cancels with this 2. So this is approximately equal to 1 upon r, 1 plus a upon r cos theta. So this is the value of our 1 upon r1. And similarly, the value of 1 upon r2 may be written as 1 upon r2 is equal to, this is approximately equal to so this is 1 upon r1. Similarly, 1 upon r2 is approximately equal to 1 upon r, 1 minus a upon r cos theta. Now we have the value of 1 upon r1 and 1 upon r2. So put these two values in this equation of electrostatic potential. let us put the value. So what we get? We get the value of V is equal to electrostatic potential is equal to 1 upon 4 pi epsilon naught is taken as common. This is Q upon R1 minus Q upon R2. So this is just put the value, then you will have 2a cos theta upon R square. Okay, on putting these two values, 1 upon R1 minus 1 upon R2. So these terms cancel out and we are only left with a upon R cos theta plus a upon R cos theta. So this is 2a upon R cos theta. So we have the final equation as, this is Q here because Q upon 4 pi epsilon we have taken as common. So this is the final equation, and if we multiply these two, we have the value of V electrostatic potential as 2qa cos theta upon 4 pi epsilon naught R square. And from the definition of dipole, we already know the dipole moment from our lecture. So the dipole moment, which is denoted with a simple capital P, is written as 2qa, because it's a charge multiplied with the distance 2a. So this is q into 2a, and so we can write P, we can replace P here in this 2qa. So our electrostatic potential may be written as the dipole moment P cos theta upon 4 pi epsilon naught R square. Right? So here in this equation we have P cos theta and the direction is r cap. So if we have two vector products and we are having a cos theta, then we can write this down in terms of the dot product. P is the position vector, this here is O and this is P, so OP is having a value of R. So the electrostatic potential V is equal to P cos theta upon 4 pi epsilon naught R square. So here we have P cos theta. This P cos theta may be written as a dot product between these two. The point P, that P is our dipole moment. So this is a capital P, which we call as a dipole moment due to the dipole. And so this is P dot R cap. So this is a capital P because capital P denotes the dipole moment of any dipole. So we can write it down as a scalar product between this dipole moment. Here is the dot which shows the scalar product. So there is a scalar product between this P and R cap, where R cap is a unit vector along the position vector OP. From point O to P, the distance is R. So along that distance R cap is a unit vector. And what is the condition we have used here? So let us put it into the scalar product form. V is equal to P dot, P is capital P, moment P dot R cap upon 4 pi epsilon naught R square, and here the distance R we have taken is very greater than the distance of each dipole from the center A. That means R is very greater than A. So this is the electrostatic potential we have calculated for any dipole, but what we have to keep in mind that this equation is true only when the distances are very large compared to the size of the dipole. The point we are taking at a distance r, and this distance is very greater than the distance between the dipole. That means our dipole is very small in comparison to the distance we are taking, and we have neglected here the higher order terms of A or R, A upon R. We have neglected here the higher terms of A upon R, and this only we can do if we impose this condition, and we get this equation. This is the first conclusion, that our dipole should be very small than the distance between the point we are calculating and the center of the dipole. That means R is very greater than A. Second condition is that if you take the dipole axis on the same axis, so the theta is 0, that means we are calculating theta is equal to 0 degree. We are calculating the electrostatic potential at the point where it is linear to the center of the dipole. Then we can write it down as V is equal to P upon 4 pi epsilon naught r square. And this may be positive or negative when theta is equal to 0 degree and negative when theta is equal to pi. That means either they are parallel to each other or they are anti-parallel. So when these are parallel, we can go with the positive sign, or when these are anti-parallel or the theta is pi 180 degree, then we can go with the negative sign. So these are the two conditions we have to impose when we are having this relation. And if we are having at the equatorial plane means the plane which is passing from the center of the dipole but is perpendicular to the, that means the theta is 90 degree, theta is pi by 2. Then if we put the value of theta is equal to pi by 2, then cos pi by 2 gives us 0. So we get the electrostatic potential as 0 for all the equatorial planes. So the points we draw from this derivation, wherever we have calculated the electrostatic potential due to a dipole, first point we have to consider is that the potential due to a dipole depends not only on the distance r, but it also depends on the angle between the position vector r and the dipole moment p. So this v is a function of r as well as v is a function of theta. Theta is angle between the position vector r and the dipole moment of the dipole p. So v is a function of r, v is a function of the distance, and v is also a function of the angle theta. Another point is that the electric dipole potential falls off or it decreases at large distances because v is inversely proportional to the square of the distance. So what we see that the electric dipole potential falls off at large distances as 1 upon r square. It is not falling off as 1 upon r. If you are having a single charge, then it falls off as 1 upon r, but in this case it does not fall off as 1 upon r, it falls off as 1 upon r square. So 1 upon r square for electrostatic potential is a characteristic of electrostatic potential due to a dipole. Next we move on to electrostatic potential due to a system of charges. But for that you have to go to our second part, that is part 2. And if you like our lecture, then please like and share and subscribe to our channel Physics Class. Thank you.